Hey everybody, how you all doing? I put these problems up last night, and I know I was late with them, but these are the kind of problems that are representative of what you should see in our homework assignments that are ongoing now for some of these, and also probably what we'll see on the next exam, which I'll figure out how to do here in a short while. The first one I want to go over, and I apologize about my writing, but this is one that I thought you might be able to work on pretty well. The first thing we're going to do is look at momentum conservation and look at this situation where we've got two, I think in their problem, they called them asteroids. They were in problem 8.31 at the end of the chapter. And what you've got here, and you've got position A on the left and position B. These are two asteroids, and I apologize for the lawn mowing going on outside. I hope you can still hear me well enough. The asteroid A is moving toward asteroid B with a velocity of 40 meters per second. I think it was right. I think it's the units on that. It was 40. And object B is at rest relative to that. So object A hits object B. So then we're asked to find the resulting velocities of A and B after the collision. What they do tell us, and about all they do tell us, is that A goes off at an angle of 30 degrees relative to the horizontal, and B goes off at an angle of 45 degrees relative to the horizontal. So what we have to do here is use conservation of momentum, and that's momentum of both objects before the collision has got to equal the momentum of both objects after the collision. Momentum is the product of velocity and mass. So in the x-coordinate, we have the mass of, oh, by the way, the masses are all equal. Makes it easy. So since the masses are all equal, then you have the mass of object A plus the mass of object A times the velocity of A prior to the collision plus the mass of object B times its velocity prior to the collision. Well, since that's zero, V is zero, that all you have before the collision here is just the mass times the velocity of A before the collision. That's got to equal, and this is a vector quantity, so this is in the x direction. You have MVA2 times the cosine of 30, because this is going to be in the horizontal direction, and velocity B2 times the cosine of 45, because this is also in the opposite direction. You can divide out all the masses because they're in both sides of the equation, and you end up with this equation just like that. And so if you wanted to at this point, you could divide both sides by this and solve for B2 in terms of A2. Let's see what else we got here, though. We got in the y direction. Well, initially, and for that matter, after everything is over, there is no initial velocity in the y direction for either one of these masses. So that's just zero in both cases. Now you have, pardon me again, you have MVA2 times the sine of 30 minus MVB2 times the sine of 45. Equate those, and you can solve for VA2 equals 1.414 times the velocity of B2. Now, knowing that, so now you've got the velocity of A2 in terms of velocity of B2. We can just plug those in to the original equation, and we end up solving that equation then for B2 and then A2. That tells us what the velocities all are. If you don't follow that, get back with me and I'll go over with you either one-on-one, or I'll do another video with a little more detail here. Now that was momentum conservation. Now, momentum is always conserved in a problem like this. That's something just, might as well write that down. Momentum is always conserved. What you'll see in this problem is that energy is not always conserved, and I'll show you how we can demonstrate that. So here is part B, and we're looking at the kinetic energy of the system before the collision and the kinetic energy after the collision. Well, we already have everything measured. So, and in this case, we don't know the mass, although the mass was equal on all of them, so it doesn't make any difference. So you have 1/2 m times 40 squared. And so the kinetic energy before the collision is simply 800 times the mass, whatever the mass is. The kinetic energy after the collision is equal to 1/2 m the squared, and so that this equals then 0.804, which is the energy of the the ratio of the energy after the collision divided by the ratio before the collision. That means you had a change kinetic energy of this fraction was 0.198, so that's 19.8%. I know it's getting too loud, but I can't do anything about it. But what that tells you is, because of the change kinetic energy, energy was not conserved in this particular problem. So you can use that and make use of that, but it's not conserved here. I hope you can hear this, and I'll be on in a minute when things quiet down with another one.